quite the era the Higgs field came into existence.
Let's go to the very beginning. In the 1970s, physicists realized the very close ties between two of the four fundamental forces, the weak force and the electromagnetic force. Now, here's the thing. The basic equations of this unified theory was able to correctly describe the electroweak force and its associated particles. But for one thing,
all of these particles have no mass in the equation. And while this might be true for photons, the W and Z bosons do have mass.
Fortunately for us, theorists Robert Rout, Francis Englert, and Peter Higgs made a proposal that was to solve this problem. What we now call the Rout-Englert-Higgs mechanism gives a mass to the W and Z bosons when they interact with an invisible field, now called the Higgs field, which pervades the universe.
And so, on the 4th of July 2012, the ATLAS and CMS experiments at CERNs Large Hadron Collider announced they had each observed a new particle. Now, simply put, at the Large Hadron Collider, two protons collided at speeds slightly less than the speed of light, and the enormous amount of kinetic energy was converted into a new particle with mass, a Higgs boson. Now, why is it that sometimes there's a Higgs field, and at others Higgs boson?
This is because as a consequence of wave-particle duality, where all quantum matter behaves both as wave and particle.
All quantum fields also have fundamental particles which are simply excitation in the field. Higgs field's associated particle is the Higgs boson.
So, what exactly is the purpose of the Higgs field?
To put it simply, Higgs field is a field that gives mass to other fundamental particles, such as electrons and quarks.
As to how that works,
just after the Big Bang, there was no Higgs field, and so the universe was essentially empty. However, as the universe cooled down, the Higgs field came into existence, growing spontaneously so that any particle interacting with it acquired a mass, where before, all the fundamental particles behaved like a photon, that is massless and traveling at the speed of light.
Now as to how particles acquire mass, well, let's see then. The more a particle interacts with the Higgs field, the greater its mass. That's supposed to be simple, right? I don't think I quite understand.
This means any particle that passes through the Higgs field distorts the field, and this distortion slows the particle down, preventing them from traveling at the speed of light. And this slowing down is the particle's mass.
Still don't understand.
Imagine a scenario in which there is a person, and that person has to cross a path, but the path is filled with other people, which is the Higgs field. So in order to cross it, instead of running like he would when the path would be empty, he would have to slow down to cross it, because of the resistance he would face. This slowing down due to the interaction with the people would be the person and in turn the particle's mass. There is a slight difference. The speed and so mass will be same for the particle, no matter which route it might take, as well as throughout its journey, and this is not the case normally. Now, the reason for the different masses of fundamental particles is because in this scenario, which follows the rules mentioned just now, if there were three people and they had to cross the path with the same initial speed, then their mass would depend on how much they interact with the people, and so in turn how much they will slow down because of it. This is why since quarks interact strongly with the Higgs field, so they have a large mass. Electrons interact only slightly, so are light. Photons do not interact with the field at all, so they have no mass.
Thankfully, after much work and efforts of hundreds of scientists, we no longer have to take its existence on faith, as it will also undoubtedly, hopefully,
open us to new discoveries and further our understanding of the unknown.